Uh, Thanks. Hi, everyone. I'm Ahmed Zaher, and today I'll be presenting our work about function merging. This is joint work with Amir, Goharshady, Kerim, Kochekov, and Tian. So let's start. Okay. Compiler optimizations, they usually aim for speed. They want to make the compiled code run faster. However, there's another class of compiler optimizations which aims to reduce size. And why would you care about reducing size? Well, there are applications where you do care. For instance, in mobile applications, you want to keep your download size small. And in embedded systems, you have very little resources, and program size can be a serious overhead. So we look at a particular code size optimization called function merging. There, you're given as input two functions, f1 and f2. And what we want to do is that we want to construct a merged function, f star, such that it captures the semantics of the two functions, and we want its size to be as small as possible because we're optimizing for size. So I'll give a running example now, and I'll make a simplifying assumption that size is measured by the number of lines. So here are two functions, f1 and f2. They both take a parameter x. And here's one way to merge them. We have this merged function, f star. It also takes a parameter x, but also takes this selector parameter b, which is when set to 1, this function will simulate f1, and when it's set to 2, it will simulate f2. I'll go back to how this function is constructed, but the point is that now we can completely remove the body of f1 and replace it with a single call to f star, and similarly for f2. And in this example, we actually managed to reduce code size before and after. It was 23 lines, now it's 22. So in this example, function merging was successful in reducing size. Okay, how do we do the merging? The state-of-the-art approach for this is based on sequence alignment. I will overview this approach for you because we build on top of it. Basically, you view the two functions as strings of instructions, and then you align some pairs of instructions across the two functions. And after that, for the aligned pairs, you just merge them into one and maintain one copy in your function. And for other instructions that say appear only in f1 but not in f2, then you put them under a condition so that they are only executed when you're simulating f1. And of course, the more aligned instructions we have, the more merging we do, and the smaller the merged function is. So let's see this in our example. Here are f1 and f2. And here is an alignment. We have these green boxes which map identical instructions in the two functions. And we also have things that only appear in f1 but not f2 here in red, and similarly for f2 in blue. And what's important about these arrows is that they should not cross. And the way we construct the merged function is we basically do a simultaneous scan of the two functions from top to bottom. Whenever we see a green instruction, we just put it. If we see, say, a red instruction, then we put it under the condition that b is equal to 1. So here it is, green instructions put as they are. This one was red in f1. Now it's put under this if condition. So it's only executed when we're simulating f1. Okay, so we want to align more instructions, and this idea gives rise to this problem, sequence alignment. You have two strings, and you want to compute the optimal sequence alignment between them. And then the bulk of this approach is to basically reduce function merging between two functions to sequence alignment over them, but viewing them as strings. And how fast can we apply this? Well, sequence alignment is an undergrad classical problem. The textbook dynamic programming solution, you can apply it here, and you'll have an algorithm with this running time, the size of the first function times the size of the second. Okay, so this is a great approach, very successful, but it has a drawback in that it sees every function as a single fixed string. Whereas in reality, you can obtain different equivalent strings for the same function by reordering some of the branches. So define this set, reorder of f, to be the set of all strings that we can get by reordering branches in f. And now we consider this more expressive formulation where we want to first try all, we want to first try all possible reorderings on F1 and on F2, and then for each choice, we do the sequence alignment and we take the best choice. And the hope is that this does better than vanilla sequence alignment on a fixed string. Okay, so let's apply this here. If we look at F1, we have this FLF with 2 branches. We can swap them to get this function, which is equivalent but syntactically different. And by doing this, we can actually get a better alignment. And we construct the merged function as before. And now we have even more size reduction. So from 23 to 22 with the basic sequence alignment approach. By adding branch reordering, we cut 2 extra lines. Okay, so all of this is just to tell you that this is a problem that we're solving. And in this paper, we look at this problem from point of view of algorithms and complexity. And our first result is a negative result, basically saying that this problem is NP hard. So before, without branch reordering, it's polynomial time solvable. We add branch reordering, now it's NP hard. So what can we do about it? We can use this paradigm called parameterized algorithms, where instead of trying to solve the problem in the general case, where it's known to be hard, we solve it on a restricted subset of the input space. In particular, we apply this framework. We identify some parameters or features of the input such that these 2 conditions hold. First, we want it to be that for inputs that we care about in practice, we want these parameters to be restricted. And we also hope that restricting such parameters would allow us to design fast algorithms, which would overcome the hardness for the general case. If we do both of these things, then we're happy. We have a fast algorithm, and we manage to work around NP hardness. And the rest of our paper is just an instantiation of this framework. So what are the parameters or features we look at? We look at branching factor and nesting depth. Branching factor is the maximum number of branches you have at any branching point. Nesting depth is how deep you nest your branching constructs. For example, in this function f1, we have this FLF, which makes a branching factor equal to 2 because it has 2 cases. If we had an f with 5 cases, then the branching factor would be 5. For nesting depth, here we have this print, which is enclosed within a for within an if, making the nesting depth 2. Okay, and our hypothesis is that these parameters are small. Their values are small. You'd expect that they are considerably smaller than the input size. So our 2 algorithms, they rely on this hypothesis. Okay, so we actually have 4 parameters for each of the 2 functions. We have branching factor of f1 and f2. Let's call them b1 and b2. And the nesting depth of f1 and f2. Let's call them d1 and d2. And our first algorithm is concerned with the case where we restrict all 4 parameters. So we give an algorithm with this running time. It's polynomial in the input size and exponential in the 4 parameters. So in general, this is not a fast algorithm. It's very inefficient. But if you restrict the 4 parameters, meaning that they have small values, then this term actually becomes acceptable. And this is polynomial, so the overall running time is efficient. And then we give a second algorithm, which gets rid of the dependence on one of the depth parameters. So instead of requiring that all of them are restricted, we only require 3 of them. So we give an algorithm with this running time, polynomial in the input size, well, worse polynomial than before. But this exponential dependence only has b1, d1, and b2, so it does not have the depth of the second function. So it can be arbitrary. This is basically a highlight of our results. And in the remainder of this talk, I just give some intuition behind the main ideas of these algorithms. So what about other restrictions? Well, for our NP hardness result, we show it for very simple case. So this already tells us that a lot of the other restrictions are already hard. But there is one open restriction where b1 and b2 are restricted, but the depth of the 2 functions is unbounded. Okay, let's get into some technical details. Here's our problem again. And the bottleneck here is this set of reorderings, which has size exponential. And we actually don't care about this set itself. We care about sequence alignment. So our starting point is the intuition that if you take the textbook algorithm for sequence alignment, it has this very nice property in that it's kind of an incremental and simultaneous scan of the two strings. So there you would have a state for that has two pointers, I and j, that go through the two strings, and then they just keep moving to the right in one direction. So we use this insight in our algorithm in the sense that we do an incremental and simultaneous exploration of the set of all reorderings of the first function and the second function. And as we're doing so, we compute the sequence alignment, the best sequence alignment on the fly. So let's give some details on how to actualize this intuition. First, we do some abstractions. We represent programs as graphs. This is basically reading the code from left to right instead from top to bottom. So we have these white nodes which carry instructions. And we have two dedicated left and right nodes corresponding to the first and the last line of the function. And for branching points, we model them with these solid nodes. So for example, we have this f_elif. It's modeled by this node here, and its two branches are modeled by these two regions below it. Okay, so remember the bottleneck was the set of reorderings. Let's try to understand this set of reorderings by traversing this graph. So we can design an exponential time algorithm, a recursive one, which does this. So it has three parameters: a currently visited node u, set of all visited nodes so far, and a string of all instructions we accumulated up to this point. The interesting case here is that if we're traversing a node carrying an instruction, then there's no branching, then we just move to the next one. We append the instruction to S and move on. Otherwise, we have a branching, so we look at all the branches that are not visited yet, and we explore all of them. So this algorithm on its own is very useful, but it reveals a very crucial insight in that the number of pairs, nodes we visit, and set of visited nodes, its size is actually polynomial in the input size and exponential in the parameters. So this is a crucial lemma of our algorithm. I'm not going to prove it, but we use it, and we also extend this algorithm to scan two functions instead of one, and also compute the sequence alignment as it computes. And now we have a dynamic programming algorithm with this many states and this much work per state. We give further optimizations to optimize the work we do at every state, and we have our theorem. I would say a few words about the second algorithm, which I think is quite interesting. So the idea behind it is that we view the first algorithm as a weighted reachability on a finite graph. And then we observe that if we take the set of visited nodes, say, of the second function, the set x2, its behavior as this algorithm proceeds mimics a stack. And the height of this stack is corresponds to the depth of the node that we're at. And this insight allows us to reduce a problem to reachability on a weighted pushdown system. And then we use classical reachability algorithm to get this running time. This is it. Thank you very much. I'll be happy to take questions.
Great. Who has questions? Let's see. We'll go Krish and then you.
Thank you. Excellent talk. Have you considered the possibility of removing branches and then performing the alignment of functions?
Removing branches?
Yes. You can eliminate some branches and then considering the possibility of aligning the functions. Or another example would be you're talking about the branch factor. So you can take your function and you can make all the branches as one-sided branches. So the branching factor becomes 1, and then try to perform the alignment. Can you comment on this, please?
Oh, you mean taking, say, 3 branches and then reduce into an f, and then in the else you put the 2 branches?
Yeah.
This is an interesting question. their views were curious also about it. So there, what will happen is that you will blow up the depth. So you see our problem depends on both the depth and the branching factor. And also by doing this, you lose some of the expressivity because some of the permutations of the 3 branches will not be achievable by doing this, this transformation. So it's kind of a balance, like using this transformation, you can do a balance to where you reach both small branching factor and nesting depth.
One more question. Are you doing this at the source level or some intermediate representation level?
Well, we don't have experience yet, but we expect that if this is implemented, it would be at something like LLVMIR.
Thank you very much.
Thank you very much.
Hi, thanks for the talk. So you focus on branch reordering here. Have you considered reordering statements that don't have dependencies, or does that have kind of similar problems of exponential blowup and so on?
This is an interesting question. It will kind of add an extra degree of freedom to the problem, and it will make it much harder. We haven't looked into, like, we don't know the exact complexity if you allow both branch reordering and reorderings of independent instructions. But yeah, this is something we might look at for future work.
Yeah, that makes sense. Thanks.
I see. Yep.
Thank you, great talk. I'm wondering if you can view this problem as a special instance of anti-unification modular equality. And my second question is, like in reality, like there are all these different equalities beyond branch reordering. So have you considered, for example, doing some parameterized algorithm over, say, an E-graph?
What's this problem? Something modular, something? I didn't.
Anti-unification modular equality, or E anti-unification.
Oh, I'm not familiar with this problem, so.
Could you comment on if it's possible to have some parameterized algorithm over an E-graphs, which is a graph of equivalencies between programs?
I don't know how E-graphs would also have this branching factor. I'm not very familiar with E-graphs, but yeah, we can discuss it offline.
Thank you.
Great. Well, we take another question. Ifan, can you start getting set up?